Evening. My name is Tom Baldwin. I'm the Dean of the College of Natural and Agricultural Sciences, and I would like to welcome you all to this evening's lecture, the second lecture in the second series, this series on global climate change. Today is a good day for a lecture on climate change. It's Earth Day, April 22nd. This is the 40th celebration of Earth Day. It's a celebration of the Earth. It's also an event to raise awareness of the environmental issues that face us all. Climate change is indeed a very urgent issue. It's probably the most important of our time. Before I introduce tonight's speaker, I would like to say a word about the Science Circle. This is a group of individuals who feel passionately about science. They're good friends of the college, and they work hard to support our programs. They support, in fact, this lecture series, and I want to thank them from the bottom of my heart. Thank you all so very much. I would also like to recognize some graduate students in the Department of Earth Science who have been helping as ushers for this series: Baird King, Joanna Asagura, Michael Trumbauer, and Cassie Mayer. Thank you all very much for your help. I would also like to recognize teachers who are here tonight. We have set up this program so that teachers can attend these lectures and obtain continuing education credits for it. Would teachers who are here in attendance please stand and be recognized? These folks are indeed our partners, and I deeply, deeply appreciate your efforts. I would also like to recognize the school board of Riverside Unified School District. I've been watching for those who come in, and I think Kathy Allaby, Kathy, didn't see, Lou Vanderstill has been attending these lectures, and I didn't see Lou come in, but Lou, are you hiding somewhere? Okay. Well, the next lecture in this series is not going to be in this room, so that's an added level of confusion. All of the lectures, save the next one, are in this lecture hall. The next lecture in this series, which is 2 weeks from tonight, is going to be held in the University Theater, where the lectures of the last year were held. So please don't get confused and come here 2 weeks from tonight for the third lecture in the series, but go to University Theater. And I'm sorry for the confusion, but that's the way it is. The lecture tonight is going to be presented by Professor Richard Minich. Rich is a professor of geography in the Department of Earth Science. He received his bachelor's degree from UCR in geography in 1968, received his master's degree in 1970, both in geography. He then traveled all the way to the west of the United States to UCLA for his PhD, which he received in 1978. He taught at Cal State Northridge and the University of Oregon before returning to UCR in 1980 as a member of our faculty. He served as chair of the department from 2003 to 2005, and since 2005 he has served as vice chair of that department. His field is biogeography and climatology. He is internationally recognized for his work in fire ecology. He's author or co-author of over 150 publications and 3 books, all published by UC Press. His most recent book, I have a copy of it right here, is entitled California's Fading Wildflowers, Lost Legacy and Biological Invasions. I was thumbing through this book this afternoon, and I think I'm going to have to keep it, Sarah, for a while, because I'm going to have to read it. Richard is known for his uncommon ability to bring multiple methods and approaches to a particular problem that he studies. He's also known for the meticulous nature of his research. Proud to introduce to you Richard Minich.
Thank you for your kind words. And it's a pleasure to be giving this lecture on a very special day, Earth Day. Well, I better put on my own PowerPoint maybe here. And there we go. The press has recently revisited the Apollo 13 mission, which brought a lot of concern to a lot of people. We had people going to the moon, and suddenly an oxygen tank broke, and suddenly these people out there, 250,000 miles away from Earth, had to live on a finite amount of resources to get back. And these resources, of course, are oxygen, food, warmth, and they made it back, but they only had 5 days to work with. Whereas we have these here on Earth, and they've been evolving this way for billions of years. And this fact, I think we should really celebrate, especially so on Earth Day. Earth is an incredible planet. It is an outgrowth of physical and biological processes that embody continual change. One feature that has transcended Earth history is its ocean, covering 70% of the Earth's surface, and was the original home of life, from which came photosynthesis, the development of atmospheric oxygen, and most importantly, it has been a great regulator of Earth's climate. The thermostat of regulation is the fact that the Earth is a negative feedback. If you warm up the world, the oceans will evaporate more and cool themselves off, and vice versa. The ocean also circulates and stores great quantities of heat. It is the primary thermal reservoir for our atmosphere. Over the past century, the Industrial Revolution and the use of fossil fuels has led to rapidly increasing our atmospheric carbon dioxide, and global warming has been a fact during this time. The physics connecting CO2 with temperature, the greenhouse effect, is mechanistically indisputable, as it was solved in the late 1800s by Arrhenius. Much is said about what humans are doing to the ocean, the atmosphere, and the climate. This question, however, is also a matter of scale and rates of change. Think of the shifting baseline syndrome. The story you tell depends on when you start the story. If you, over geologic time, if we start over long periods of time, we could ask the question, have we gone through climatic change of the magnitude predicted for our future? In the first part of this presentation, we will look at the past 65 million years, and we'll see that the climate was warm and then has cooled to the modern ice age and has warmed recently in the last 10,000 years, with huge effects on landscapes and the biota. It is important to understand how our climate and vegetation has come to its present state. Another question is what will happen to future climate. Predicted CO2 levels will be comparable to greenhouse climates 65 million years ago, but will phase with our modern ice age ocean. Will we produce a new climate never seen before? One problem is how this energy is stored in the ocean atmosphere system. But unfortunately, the science around this problem lacks clarity. Computer atmospheric models that predict warming are only recently being linked to the oceans, and we need to evaluate how energy is circulated and stored in the ocean and how that has affected recent climate change. And finally, now biologists are modeling vegetation and species changes of the future. But this uncertainty is even greater in biology, as nature is always full of surprises. In the last section of this talk, we will look at changes in California landscapes and the biota in retrospect, not in forward modeling. So let's go to the first part here and look at the last 65 million years. If there's anything I learned about hanging around geologists, is that they can take a perfectly solid planet and turn it into silly putty. And there it is, rolling around. And of course, this represents one of the great scientific breakthroughs in the 20th century, and that's plate tectonics. We can move the continents around, that's one finding. But even more importantly is that the motion of the continents through time changes climate. And what we look for is if you have your continents concentrated in lower latitudes and oceans largely dominating the polar regions, you will get a warm climate. And as you can see from this cycle of about 200 million years, it has changed from one to the other. This is a profile of estimated temperature from 65 million years to the present. And it is based on oxygen isotope data, and I'll explain that here in a second. Little organisms that make shells that live in the oceans drop their cells after they die, and the shells are accumulating on the ocean floor. And we core the ocean floor, pick up those shells, and we examine the ratio of oxygen 16 and 18. And that ratio gives us an indication of how warm or cold the climate is. And the profile is that it was quite warm all the way up to about 40 million years ago. It's been steadily cooling in leaps and bounds, but especially over the last 14 million years. So the geologists are using two terms to describe climate change in this frame of reference: icehouse climates and greenhouse climates. And the kind of things you look for in a greenhouse climate is to drown your continents. For example, a lot of Europe is underneath water at this point. There's a seaway in Africa. And your continental pieces are largely in low latitudes, and you've got a lot of ocean in the high latitudes. And in an icehouse climate, you don't want your continents to be drowned. You can have land masses that heat up and cool off rapidly, have them crowd around the pole where there's less light, and so you can cool off the world more readily. In terms of the previous figure, what causes the change in the oxygen isotope ratios is the fact that during these warm worlds, most of the deep water is produced by evaporation in the subtropics, and that water sinks down to the deep sea. And if you go to the icehouse world, then it's actually melt from ice sheets from both poles that forms the deep water that was measured in that profile. So I'm going to give you 3 snapshots of the past. And we're going to have our first snapshot at 50 million years ago. And we had a same kind of current, ocean currents as we see now, except that the current off the west coast was warm. And I show it in red. And this was a warm world where the polar ocean, the deep sea temperatures below the Lida zone in the darkness of the deep oceans were as high as 12 Celsius, 55 Fahrenheit. And I want to emphasize to you, because of that the polar oceans cannot be less than 55. Even in the middle of winter in the poles, when the sun is set for 3, 4, 5 months, the waters that chill at the surface of the oceans of the poles will chill and sink. And the reason is water reaches its highest density of a temperature of about 5 degrees Celsius or 42 degrees Fahrenheit. Water that's either warmer or cooler than that will in fact be denser. And so the 55-degree water will chill, get heavy, and sink. And so imagine, being a penguin at the South Pole, and then your ocean temperatures are 55. Now, the world here, and I'm going to emphasize North America mostly, and looking at the plant fossil record that suggests that we had a very warm world at that time. And then we will focus more and more as we approach the present toward California. So we are now about here with respect to the following slide. So what did we find? Well, we can go to Ellesmere Island, and this is latitude 80. And we had cycads, flying lemurs, of all things, crocs, and turtles, a very tropical kind of environment right up to the North Pole. And if you go to the Bering Strait, there's huge fossil records in many localities there. They have the ordinary deciduous trees that we're familiar with, that you find back east, for example. And there are also tropical trees with drip tips and an entire leaf like this without toothing. And this is, how do we know it's tropical? Well, drip tips are associated with tropical vegetation now. And the reason, in the tropics, decomposition is so fast that if you don't shed your water quickly, the decomposing organisms will destroy the leaf while it's still alive. So you shed the water as fast as you can. Not so important with these guys. And this is all the way up to the Bering Strait. We were seeing tropical plants. Going to the western United States, we had dawn redwoods, which in modern times is only found in China. Sequoia, we had coast redwood. By the way, the coast redwood was known in just California and the west. It was all the way to France. And we had, and many of these pictures I will be showing you fossils and associated with the living plants. And this is a stump of coast redwood in Montana. Also in the western United States, there were many deciduous trees, ginkgos, liquid amber, or sweet gum, linden trees, maples, sassafras. These are things we find back east in the eastern United States. And tropical things. There were fig trees in the west coast, as far north as Oregon, and camphor trees. And just picking out liquid amber of all these, it represents the other species. Most of them are presently found in the southeastern United States and Southeast Asia and China, in areas where there's warm and wet with as much as 30 to 60 inches year-round. And yet the fossil records find liquid amber also, portions of Europe and here in the West Coast 50 million years ago. Now there were mountains. The Rockies were already up, and so there were cooler climates there. And they found spruce and fir and Douglas fir, things that are ancestors to the modern conifers here in California, pines. And if you go far enough south in the Rockies, actually arid forms were found in the chaparral. The ancestors of chaparral go back to the 50 million years ago. Things like mountain mahogany and scrub oaks and buckthorn and coffeeberry. So our chaparral actually has roots that go back 50 million years here in California. Going briefly to the southern hemisphere, I'd like to refer to the work of Mike Woodburn, emeritus faculty in Earth Sciences, who was the first to find a fossil mammal on Seymour Island. And again, it's 50 million years ago. It was kind of a marsupial rat-like creature living in the southern beech forest, which was covering Antarctica at the time in this very warm world. And now we're going to fast forward to the Miocene, which is much later. You'll see the age. This is 50 million years, and now we're going forward to 14 million years ago. And going back and forth, you think that the continents are changing quite a bit. The flooding of Southeast Europe has ended. He lives it there. The continents are sort of crowding northward to the North Pole. We still had an open seaway here, so the waters of the Atlantic Ocean could just flow into the Pacific. And Australia got smart and moved away from Antarctica, okay, see where it was. And India here was running itself right into Asia and started forming a continental collision and the formation of the high mountains of Tibet. Now, at 14 million years ago, the DC temperatures are now down to 6 from the 12, or about 44 Fahrenheit. Quite a bit cooler than down here. But this is a temperature where water will still float in the Arctic Ocean. So you cannot form, or it will not float, it will sink if you chill it in the polar night. So you can't form pack ice in the Arctic yet. It was still an open ocean. And what was found in the western United States? Okay, deciduous trees that we don't see much anymore, just as in the much earlier periods. Walnuts, we still got them. We have maples, elm trees in the west coast, wow. Chestnuts, magnolia. And the same conifers, they're no longer in the Rockies, they've marched across the Great Basin and have now colonized the newly forming mountain ranges, the Cascades, and the Sierra Nevada on the west coast. So we still have spruce fir and Douglas fir. And here are the fossil pine trees that are just hanging out in pinyon country in Nevada. And pinyon pine starting to form, giving evidence of drier climates that are beginning to form in the Great Basin states about 10 million years ago. We think of the big tree redwood as only in the Sierras. Well, it was all over Nevada during the Miocene or 12 million years ago at this point. Again, unmistakable foliage of the big tree. And there are other newcomers, madrone, old world laurels, canyon live oak, a modern species pretty much, and oaks. More drought tolerant things are starting to enter into the scene. And chaparral had arrived, and 10 million years ago onto the west coast, and many of the things we commonly see in our mountains, chaparral cherry, toyon, manzanita, ceanothus, and sumac, sugargrass sumac, their ancestors were already here. And they represent a drying of the climate, but most specifically, the drying of the climate during the summer. And one good evidence, and I'm going to make several references to the GEC program, the Global Climate and Environmental Change Climate Program in our department, is Joanna Oseguera is working on the Wachovia Lake sediments, which is a former lake in Owens Valley, and was able to find certain kinds of organisms that are salt tolerant, which suggests that this former lake was in fact an enclosed lake and not spilling out and getting saline even 3 million years ago, which means that the Sierra Nevada are already rising, forming rain shadows and starting to make the region more arid. So now we're going to fast forward to the ice ages, and you can see the continents are still crowding northward. The Atlantic is opening out, and very importantly, we got a Panama connection through here. And Antarctica is in full-blown glaciation and has been since 10 million years ago. It's been pretty much a solid ice sheet for that period of time. So now the California current is cold, no longer warm, and the deep sea temperatures are now down to 36 to 40 degrees. We are here now in the modern times. Glaciation and cold ocean currents and Mediterranean climate are strange bedfellows. You get a deep sea that's cold because you get the melt off an ice sheet. And then you upwell cold water from the surface and you generate a cold ocean current off the west coast. And that cold ocean current kills rainfall in the summer. So voila, summer drought. And we've been in that now for 10 million years, but becoming ever more intense in recent times. And what are other reasons for glaciation? Antarctica is well placed. It's isolated over the South Pole. And we have the rise of the Rocky Mountains in the Sierra Nevada, which isolate the interior North America from the warmth of the Pacific Ocean. The mountains from Asia that have formed with the continental collision and extending toward Europe are isolating northern Asia from the warmth. And the Panama connection is taking warm waters of the Atlantic and shoving it north as a Gulf Stream towards the high latitudes of the Atlantic, and has been the source of ice sheets that have developed in Greenland, Canada, and Scandinavia. So with this new climate, there are winners and losers, and the winners are the things you see now. In the lower elevations, we see grasses and forbs that can be annual and survive summer drought, and we can have drought-tolerant trees such as oaks, some deciduous like the valley oak and the coast live oak, it's evergreen. In the lower hills, you'll have chaparral. And in the mountains, we have evergreen conifers, which are also very drought hardy. What are the losers? The deciduous trees. And unless you're near a stream, they're gone. And this rich flora that was recorded over most of the last 50 million years has disappeared, except for things like maples and alders and willows along the streams. And the tropical stuff is gone. And the most tropical flora we still have in California is found in the deserts. I want you to pay really careful attention. Think about this picture. This is only 20,000 years ago. It's like 300 generations of humans, okay? And we have an ice sheet covering all of Canada, an ice sheet extending from Scandinavia to Russia, and the ice sheet of Greenland. Only 20,000 years ago. And it has since retreated to the modern conditions. But it's been oscillating back and forth from these two states now for about 1 million years. What is the cause for these oscillations? And the oscillation is seen in these oxygen 1618 estimates of temperature. It's zigzagging all the time. And we're right about there. Now, it's always zigzagged. It's now getting amplified because the oscillation is getting more and more involved in the building and collapse of ice sheets. We had no ice sheets in this period of time. And what's causing this cycle? It's about a 100,000-year time frame. Our three orbital characteristics. One is the tilt of the Earth. It's varying between 22 and 24.5. The ellipticity of the orbit ranges from highly elliptical to perfectly circular. And finally, we have precession of the axis. The Earth is wobbling around. Right now, the North Pole is pointing to Polaris, the North Star, but that won't last. It'll point to some other star some 10,000 years into the future. They have three different periods, 40,000, 100,000, 23,000, and they all phase every 100,000 years together. But these orbital properties result in amazing variation in the amount of light that can be absorbed in the northern hemisphere in particular at high latitudes. It's plus or minus 6%. It's significant. And when you can get a situation where all these three phases come together to maximize light during the summer in the northern hemisphere, you can wipe out an ice sheet. And if it's otherwise, you can form one. And in fact, here are the last two. We're in an interglacial right here, or the last 10,000 years. The previous one is about 130,000, 120,000 years ago. And here's our temperature profile going up and then going into the last glacial and then coming up into the modern climate. And from sea ice cores, we get other information that Martin Kennedy talked about last time. You can get annual layers of ice, and you can get trapped air in that ice, and inventory how much carbon dioxide is at that time. And the CO2 was higher during periods of warmth and lower during periods of cold. Methane is kind of resembling that, although it's not as clear cut. And dust is also much more abundant during glacial episodes than what we see now. The world during a full glacial is a really windy place. The wind circulations of the jet stream and the trade winds were much stronger then than now due to the great differences in temperature between the equator and the poles. And the wind was blowing dust all over the planet, and it was collecting in these cores from Greenland in this case. But even beyond the 100,000-year scale, we have these millennial or 1,000-year scales of spikes going up and down during the Ice Age period, and not during the modern period. And what is going on here are these tremendous cascades of ice flow that go from the ice sheets, that go into the ocean. And you get these armadas of icebergs. And once the ice sheet starts flowing into the ocean, because it's soft, kind of not very strong rock, if you please, the ice keeps on flowing into the ocean. It can't stop itself until it thins down enough that it does stop itself. And these cycles operate in 1,000-year intervals. And it's sometimes the ice, there's so much cold water that's driving out into the Atlantic Ocean in particular, that the Gulf Stream is headed south beyond current conditions. And then when the ice quits flowing enough, the Gulf Stream swings back north, and then we get into these little warm spikes. We have these names for them. Take them for what you Heinrich events and Donskar-Oskar cycles. And Cassie Myers is looking at the core of Owens Lake to see if these kinds of cycles are being recorded in California climate at about 500,000 years ago. Also, when you have a reflective ice sheet, you drive the jet stream much farther south than what we see now. And it was dislocated down to our latitude in California. It rained a lot more. We probably had twice the precipitation in an ice age than we do now. So Riverside would have 20 inches, Los Angeles about 35 annually. And the mountains here would be up to 60 to 100 inches a year. And because there are more storms, like we had last night, going through California during the winter season, the evidence of wetness in our climate is the spectacular glaciation of the Sierra Nevada. It wasn't just mountain glaciers, there was actually a cap ice sheet on the crest of the range, all the way from north of Reno, clear down to just past Whitney. And it sculpted these beautiful U-shaped valleys and these razor ridges, this spectacular topography that we're used to in our Sierra Nevada national parks, such as Yosemite. All these features we're familiar with for those who have visited our base, created by ice sheets that had developed many times, but most recently 18,000 years ago. And don't forget our backyard glaciation. San Gorgonio Mountain had 10 glaciers on it. Here is one of them, and it was forming up here and spread down a couple of miles, and was most extensive, only 16 to 20,000 years ago. And other evidence of wetness, we had huge lakes all across the Great Basin as well as the California deserts, fed largely by rivers that are coming from the wetter mountain areas. So the Owens River was feeding Owens Lake, Ciro's Lake all the way over to Panamint Lake, but not really into Death Valley. And the Mojave River was feeding down towards Soda Lake, Silver Lake, and down to Lake Manly during a full glacial. If you look at the shorelines and carbon date the shorelines, we can reconstruct how high the lakes were at various times. And in our region, basically the lakes were high all the way from 30,000 years to 10,000 years ago, and then they dried very rapidly at the end of the last ice age. How else was it wet? Go to the La Brea tar pits. Wow, there are fossils there. Not only that, but we had Monterey pine and Bishop pine here. They're found farther north along the coast. We still have Coulter pine. Our mountain forests were extending down to lower elevations than we see now. Coast redwood is recorded at the tar pits. Douglas fir, there's a log that became eroded out in western Santa Cruz Island down here. The southernmost real stands of Douglas fir is Big Sur, so this is a southward extension of some 200 miles down the coast. And we also used to have gray pine. It's found now in the Central Valley, but it was down here in Riverside. It's found in well logs in the Paris Plain. Tecate cypress, and this makes you understand how complicated this world is largely found south of us and spread north up to here during the full glacial time. And then we have our old friends of Southern California. They're also recorded down here as well. Cottonwoods, manzanitas, coast live oak, and sycamores. And then pack rats gave us this fabulous record of the plant cover in our deserts over the last 25,000 years. These guys make middens, big woody nests, and some of them show up underneath rock shelters or in caves out of the weather, and they're as old as 25,000 years. And in general, what they record is that our deserts that we see now, like this, looked like this, pinyon juniper woodland, during the last ice age, in a wetter climate and a cooler climate. Now, our ice sheets collapsed, and they collapsed in a hurry. And it's interesting how the vegetation chased the ice sheets. I want to emphasize during the collapse, which is occurring right here at about 11,000 years, And then we get into this modern climate that we're in over the last 10,000 years. But do note that the climate was reaching its warmest value about 8,000 years ago. It's been a steady, slight cooling, very slight, since that time. But what happened in here, and we'll look at the other pieces of the Holocene later, is that a phenomenal literature of pollen records from lakes in the eastern United States has you can reconstruct the distribution of various genera as they move northward after the ice sheets retreated. But this is, again, how you have to be very careful to infer climate and vegetation, is that the oaks actually move very fast because they're aggressive pioneer species, and the beech, and reaching Canada by 8,000 years ago, where the beech is also kind of like sterile ground, but moved up a little slower, reaching Canada by 6,000 years ago. And then there are trees that like to live in the shade of other trees, and they just creep northward, and they hardly ever made it to Canada. So there's always lag effects, and you've got to evaluate each tree one by one in terms of its ecology when you're trying to evaluate its relationship to climate change. And there's also lag. You know, the climate may be instantly better, and it sort of did that 10,000 years ago, but sometimes the only thing limiting the spread of the species is its own seed dispersal. That can slow it down too. And here's another case of that. The pack rats discovered this one, and that is that there's middens in Death Valley, and they show that the brittle bush, which is the dominant shrub here in our hills back of campus, moved ahead of creosote bush by 3,000 years. This is effectively a weed with long-range seed dispersal and just ripped north as soon as the climates became warm. But the creosote is a long-lived shrub that takes its sweet time moving northward. And the pack rat middens also recorded all the wildflowers that we have in our desert. And one of the greatest surprises I had when I did research on this book is that the flowers of the Pleistocene are the same as the flowers now. They didn't move at all. And the reason is they live on seed banks, and they survive periodic drought by just falling to the ground and then waiting for the good times to germinate and form good flower years. And there's no mechanism for really rapid dispersal. So they just lag behind, and they're staying in the same place in the modern climate versus that 12,000 years ago. This is the great bloom of Death Valley in 2005. It was absolutely amazing. A very wet year. Then finally, what about the megafauna? This is a very interesting story, and it's controversial. Is it climate change? But what did we have? A huge megafauna only 12,000 years ago. We had bison and forms of horses and another kind of bear, mastodons and mammoths, saber-toothed cats, rhinoceros-looking thing, camels, you name it, we had it. And they've gone through climate changes like this in the past, but why did they disappear this time? And this gets to Paul Martin's Pleistocene overkill hypothesis. And that is simply the people from Asia finally got through and discovered the Americas 12,000 years ago and raced on down as big game hunters and really probably ran into a bunch of animals that weren't afraid of them, and it ended up to be a slaughter. What are the vegetation effects of Holocene climate? A little bit warmer here, okay? Well, one of the interesting things, you go to the White Mountains, is that there are dead standing trees that are above the existing tree line. Is this some former tree line? Well, you can cross-date the trees, their annual rings between these guys and the living ones down here, and remember, they're thousands of years old. And we find out that these were trees living way back here 8,000 years ago, and they're still standing. And representing a tree line that was 50 to 100 meters higher than present in a slightly warmer climate 8,000 years ago. Are our mountain glaciers remnants of the last ice age? And interestingly, it's a recent finding, but basically the answer is no. It appears that the Sierra Nevada glaciers had completely disappeared in the early Holocene by 8,000 years ago. And based on cores in lake sediments, okay, you can get the unique sedimentary signal of the grinding of ice in the form of silts. And you can core in there and find silt layers, as well as ordinary sediments. And the first breakthrough on this was by these guys, and they were able to show the Mount Conness Glacier, which is not too far from Tioga Pass, formed at 3,200 years ago, and it got down this far. And the Palisade Glacier formed also about 3,500 years ago, and its greatest advance is only 150 years ago in what we call the Little Ice Age. And Baird King is working in Rock Creek near Bishop, and he's cored lakes here and got the signal of glacial sediments at 1,700 years to about 600 years ago, on and off, in areas that currently do not have glaciers, but obviously supported them at times like this, not too far back in our past. Small bodies of ice had formed up there somewhere in the top of this basin. Other ways in recent glacial history is kind of interesting, is that we had a medieval warm period about 1,000 years ago, and it went into the Little Ice Age, which was like from the year 1400 to 1800. And evidence is that if you lived in Iceland at the time, records of sea ice was rarely observed 1,000 years ago, and it increased rapidly 1,600 to 1,800 years ago, then dropped off in the last century. And people in Japan have had cherry blossom festivals, and they record the time where they flower. And the blooming season was postponed in this period and came earlier in this period. It's a 1,100-year record in Japanese manuscript data. And in that medieval warm period is the time when Mesa Verde was abandoned. It's possible that the Native Americans who were in maize cultivation ran out of water and had to leave. Could have been other issues, like, a nasty other tribe just kicked them out. The Vikings tried to colonize Greenland and graze sheep, and eventually the winters got rough enough during the Little Ice Age period that they had to abandon the area. And the Inuits are still there because they relied on a mammal resource, a marine mammal resource that was far more reliable than sheep on pasture. So this gets us to the current climate and what has happened over the last century. So the bottom line is, yes, we've had global warming and CO2 increase. And the mechanism is indisputable. So we have for the Earth to have a stable temperature, the amount of energy coming from the sun has to equal the energy that the Earth radiates back to space. If you add carbon dioxide, you will trap more of the energy here. And in order for the Earth to equalize everything, it has to warm up in order to radiate the same amount of energy out that's coming in. So that is the mechanism that Arrhenius had figured out in the late 1800s. But there's an interesting pattern, and this warming is in leaps and bounds. And there's a bound and a leap and a bound, and we'll pay attention to these two. From 1940 to 1977, the globe actually was in a period of subtle cooling, and then there was a rapid warming after 1977. And a lot of my comments we're going to look at before and after 1977. It was kind of a magic year. The overall pattern in this period of warming is one in which the warming is largely restricted to the northern hemisphere, especially over land and over the Arctic Ocean. And it's least over the oceans, where you get the greatest amount of evaporation, which is a feedback against warming. And there's a little bit of cooling going on in portions of Antarctica. So it's an irregular pattern, but it is a net warming. So first of all, we need to have the history of global climate modeling. The models were developed for weather forecasting in the middle 20th century. And at that time, people were concerned about forecasting. They were not concerned about oceans. So that's where the models started and the measurements started. And only recently have we gotten into coupling the atmospheric models with the oceans. And that part of the science is not nearly as advanced. But the first great breakthrough in understanding that the oceans have significant effects on the atmosphere was the discovery of the El Nino effect. And the El Nino, as you just had seen, was one where you get these spectacular warmings and coolings along the equator in the East Pacific Ocean, from the date line to Peru. And when it's in this state, where the ocean temperatures are below normal, we are in what is known as a La Nina, which is this state here. The convection and rainfall from clouds is always finding the warmest water in the tropics. And in this state, it's over here near Borneo, New Guinea, north of Australia. And if you go into the El Nino state, which is the first part of this little movie, the warmest water actually shifts eastward toward the dateline, even east of the dateline. And so the maximum convection is going on there. And it was discovered by Jakob Becknes, who I actually met once at UCLA, that he worked out this mechanism. And when the warmest waters are in the far western Pacific, the energy from it moves poleward and joins the jet stream in the West Pacific. And then the jet stream tends to ride north in the northern part of the United States during the winter months. And when the energy is moved eastward, when the waters are warm near Hawaii, then it joins the jet stream there and dislocates the jet stream southward along the southern United States. And here is a map of the precipitation departures of 8 different La Ninas, and they all show you the same signal. The rainfall is above normal in the northern parts of the country and tends to be below normal in the southern parts of the country. And that's where the jet is. And then in a year like this year, which is a pretty strong El Nino, it tends to be the jet stream is farther south and it rains hard in the southeast United States, Arizona, California, and the southwest. It tends to be dry in the northern parts of the country. This is the El Nino cycle since 1950, and here's our 1977. And it's kind of interesting. We had a lot of events, but they go about 4 years apart, and that's what's pretty typical. But we had a lot of La Nina conditions shown in blue during that period. And since that time, we've had an abundance of El Nino, or certainly warm Pacific Ocean since that time. There was a distinct shift that occurred in 1977. And here's the shift is showing in relation to rainfall in Los Angeles going back to 1950. And the thing is that there's just as many dry years, and they're generally about the same level. But we've had a lot more huge rain years since 1977 than before 1977. And in fact, the mean annual rainfall in Los Angeles has increased a little bit over the last 30 years. And moreover, this El Nino index has been correlated with what we call the Pacific Decadal Oscillation. It's a bit of a mouthful, PDO. And this is the index of the oscillation, which is described here. But it was largely in a negative state to 77 and largely in a positive state since that time. What happens is it's affected by the spin rate of the Pacific Ocean currents rotating clockwise. And when you're in this state, the negative phase, the spin rate is going up. And what it does is bring more water up from the West Pacific into the Gulf of Alaska, and it brings more cool water down into the latitude south of us, reducing the differences in temperature in the Pacific by latitude, and that tends to weaken the jet stream and make us dry. And it's all the reverse in the other thing. You decrease the spin rate, and you have more water in this, cold water at this end, and it gets warmer down here. The jet stream strengthens, and it rains more. And so, actually, one idea, and there are more El Ninos in periods of global warming than periods of steady state. And one idea is that when you have a large El Nino like this, you get more Pacific in convection, that is, tall clouds and rain, putting heat into space, compared to La Nina conditions where the convection is restricted to the West Pacific. So it's believed that the El Nino is a response to global warming by increasing equatorial convection and heat loss to space. It's an increased efficiency of sweating out the extra heat to space from the Earth's surface. Now moving to the Atlantic Ocean, where here we are trying to trace where this heat is coming from global warming. There is another oscillation called the North Atlantic Oscillation, or the NAO. And one end member of the, one stage of it is the jet stream rides north into northern Europe. And the rain, it gets wet and warm in northern Europe and actually warm and dry in southern Europe. And then the other phase, the jet stream, goes southward into the Mediterranean. It tends to get very cold in northern Europe, but dry, but it's wet and cool in the Mediterranean. And this index is shown here, and it gets into steady patterns scaling over a decade or two. And we were in a largely negative phase during the 1950s, 60s, up into the 70s, 77. And then we went into a positive phase during this period of global warming leading up to the present, although it is now shifting negative in the last few years. And related to that is this decadal, Atlantic multi-decadal oscillation. Meteorologists love to talk about oscillations. AMO. It's this brown line, and it's the same thing I just described. Here's 1977. The Atlantic Ocean and sea surface temperatures have grown warmer since 77, and they grew cooler from the 40s till the 70s. And here the green line is the global temperature average. And probably a lot of the signal of global temperature increase is largely embodied in the Atlantic more than any other part of the world. And what does this signal do to you? Interesting effects. It affects hurricane frequency. So when you get into cool phases, it actually suppresses the formation of hurricanes in the Atlantic. And it was very active in the 60s and 70s, and recently in the 90s and the 2000s. And it also affects sub-Saharan Pacific precipitation. Actually, I skipped a slide, didn't I? If you get into the positive phase in warm North Atlantic, there are more hurricanes coming into the United States. And you go in the opposite phase for another 20 different year period, it actually reduces it. So there's tremendous. We're now in a very active phase. It has been so for about 10 to 15 years. And then moving on, it's related to rainfall and how far north the monsoon enters into the Sahara Desert. And here's rainfall from this district. It's a phenomenal relationship. Here's the cooling of the Atlantic and the warming, and here's the wet years, the great drought that caused extraordinary famine. Millions of people died in this sub-Saharan Africa, in the Sahel here, and then they've been wet here for the last 15 to 20 years. Okay, that's from the ocean standpoint. How else can we affect climate? Well, we can do it from above too, and one idea is we're making our clouds. We call this global dimming, but we make contrails and we make cloud tracks in the oceans from jets and ships. And it was discovered, 4 different people from 4 parts of the world saw that pan evaporation rates, pans where you're just evaporating water out of them, worldwide had decreased over the past 20 years. And then came 9/11, and you know what happened then. We cut off all aircraft for 5 days in the United States, and instantly a unique signal showed up where the day temperatures got warmer and the night times got cooler, just for that brief period of time. We apparently have a real effect on the daily range of temperature, although its jury is out in terms of what it's doing to change the global temperature. Nature can affect the atmosphere in a very vigorous way. Mount Pinatubo being the last great eruption. It put out 15 cubic kilometers of ash, plus the sulfur. The ash is not really what cools off the climate. Everybody agrees that eruptions cool the climate for a couple of years. It's really the sulfur that comes out, and it forms sulfur dioxide. In the presence of water, it forms sulfuric acid clouds that last for a couple of years because they're up in the stratosphere where there is no rain and no clouds. It takes a long time to dissipate that cloud. And the energy is being absorbed up there by these clouds makes less for down here, so we cool off. Now, one thing that's interesting is how frequently we're getting these eruptions. And to be honest with you, the 20th century has been really kind of quiet. We've had very little material suspended in the stratosphere. Whereas in the 19th century, we had Tambora and Krakatau, and those two together account for 600 cubic kilometers of material, which is an order of magnitude anything greater than what we've had here in the 20th century. And the global cooling was far more spectacular, especially with this eruption and also with Krakatau. So one reason we might have warmed up a little bit in the 20th century is there's just been less eruptions. There also was a lot of activity in the 17th century. And that's my picture of Pinatubo 2 weeks after. This is a good hour after sunset. bloody red sunsets. Another effect is the Sunspot Cycle, which is this 11-year very regular cycle, but only once we got space platforms where we could measure it, we were able to show that when you're in periods of high sunspots, like here, here, and here, there's actually more radiant energy arriving to the Earth from the sun. A couple of watts, it's not that much, but there is a variability, so this will be low sunspots, high sunspots, and so on. You say, why? Well, these are dark things. There should be less light coming from the sunspots. The answer to that is that the area around the sunspots is actually a lot hotter, and it outcompensates for the dark areas. So that's why there's an increased amount of energy. Excuse me. Sunspots also have increased over the last 2 centuries. And so there have been estimates of how much increase in radiant loading have reached the Earth's surface over the last couple of centuries. We had actually whole centuries or half centuries where there were no sunspots whatsoever. The sunspots completely disappeared until they got active again here in the late 18th century. We are in the minimum sunspot right now, and we had the longest period without sunspots in about 100 years, last year going into this year. The sunspots are now starting to pick up. So the last year we've had less light than usual reach the Earth's surface. Sunspots also affect cosmic rays. You think I'm kind of wild. Well, they do here. The cosmic rays are coming from deep space, and they actually charge the entire atmosphere. It's slightly charged, the whole atmosphere. When the sunspots are active, the solar wind keeps the cosmic ray particles from getting into the atmosphere much, and then vice versa. And the effect is that when the cosmic rays do get into the interior of the Earth, there's actually a little more efficiency in cloud production than there would be then in the opposite phase. So some people suggested that we get a little more cloud cover when we get into these minimum phases that would be reflecting like the space. But clouds are very, very tricky to estimate how it affects radiant loading. So how well do these annual and decadal trends predict extreme events? I think you'll enjoy these. This is January 18 through 25th, 1969. Oscar Clark got to remember that one, and a lot of us with gray hair probably remember this event. These are some of the earliest satellite pictures. They only began in 1964. And it shows the jet stream in California and these phenomenal storms that are tracking moisture right from the equator right into California. And the rainfall over an 8-day period, Riverside, 7.5 inches, LA, 14.5 inches, Mount Baldy, Lake Arrowhead, 50 inches in 9 days, okay? And this developed twice, and we got these precipitation rates were absolutely amazing in 24-hour rates. I'll tell you in a second. And we had these scenes. Here's the Interstate 15 going over Cajon Pass. There's more water in the Cajon Wash, which is normally dry, than the Colorado River at this point. And in Lytle Creek Ranger Station, which is this right over this hill, recorded 24 inches in 24 hours on January 25th, 1969. And the Santa Ana River, where people accuse us of misnaming our town. And there it is, on that day, bank to bank. It went over the levees and flooded lots of areas between town and down toward Corona. Great floods, are they predictable? You say, well, of course they're related to El Niños. 1969 was a weak El Nino. It had nothing to do with it. Actually, we have another oscillation called the Madden-Julian oscillation, I think, but I won't talk about it here. The 38 flood, which killed 300 people in Los Angeles, took out bridges and everything, was a La Nada, right? A nothing. It wasn't even an El Nino or a La Nina. Likewise, 1916 flood, same thing. Krakatoa produced the flood of 1883-84. And the greatest flood of all, 1861-62, of all things, was a La Nina, according to Charles Pike. So it's not very predictable, and I guess that's my point. Extreme weather events cannot be predicted long range because they are rare. Here you must rely on weather forecasting. Here you're looking at Katrina, just about to reach New Orleans, And I might add, the Weather Service models absolutely nailed this perfectly, 3 days in advance. And people had 72 hours to get the hell out of the way. So what has been the effect of global warming on California landscapes? A lot of people are predicting forward. I don't. I want to know what has happened to California over the last 50 years. So let's look at glaciers first. Here's a Darwin Glacier. It's kind of opposite Bishop. The peak here is 13,900 feet. And in 1908, and these pictures were taken by this fellow Basagic. Well, he didn't do that one, but the latter ones do that. But anyway, he found these same places to the right rock, I might add, so he was good. So here it is, pretty good-sized glacier. The ice is right up to a moraine, which is a rock pile left by the ice. And you can see how it's retreated enormously. And the Mount Lyell Glacier, which is in Yosemite, quite a bit larger in 1903 than 100 years later. So they decreased. Here's a surprise. They decreased before 1977, mostly, not after 1977. Why is that? Well, the global warming period is over here, but temperature doesn't melt snow. It's light that melts snow, and the light is always the same. What has happened is that we've had more precipitation since 1977, which has improved the mass balance of the Sierra glaciers compared to what was going on in the middle 20th century. They're still losing a bit, but it's not the same mass loss that was going on earlier. In general, glaciers are retreating throughout the world, both in the tropics, here's Kilimanjaro, and in Alaska. And Al Gore talked about the Grinnell Glacier retreating. And to be fair, he's not telling you the whole story, and it's true with many of the glaciers, mountain glaciers throughout the world, is that by the time the first pictures were taken, when we finally had silver halide film to do this, the glaciers are already in retreat. So there was a process going on before fossil fuels that was bringing the glaciers down. And no doubt the fossil fuels have added to the problem, but there's several natural and unnatural processes that, or let's say anthropogenic processes, that are reducing the amount of ice on that glacier. I got to say this, Grinnell is a famous ecologist in California, and my father knew his son. There are a few places in the world where glaciers are actually advancing. The most important one, I suppose, is New Zealand, where the Alps, over the last 10 years, have had advances, 48 glaciers. Mount Shasta has been advancing since the middle 70s, and also some of the other Cascade volcanoes, also in Norway and in a few places in Argentina and Chile. They all have in common position in the jet stream in a very wet climate, a climate like Seattle, let's say. And I'm not saying it's necessarily global cooling that's producing this. You can have the same temperature air mass and just strengthen the jet stream. You can put more snow on these mountains without changing any other properties. That's my best guess, is that jet streams have strengthened in the northern and southern hemisphere to produce these local increases. But bear in mind, this is the minority. And then where people have become concerned, are we going to lose Greenland as an ice sheet? And the question you need to ask is, why is it Greenland has an ice sheet and Canada and Europe does not? Very interesting question here. Now, this is a huge ice sheet. It's up to 10,000 feet in depth, and it's right to the border of the island. There's ice. And it's gone here, and it's gone here. First question to ask, can you melt an ice sheet from above? And I'm going to convince you the answer is no. One of my favorite websites that you should write down in your notes right now is just go say South Pole Webcam and watch it every day. And here it is in the middle of summer. You're at an altitude of 9,200 feet. And on the warmest days, it gets to -5. You're not going to melt any snow that way. And moreover, It's the only time that you get enough sunlight that you can actually add energy to the surface lasts for only 8 weeks, okay? From the 1st of December to the last of January, because we got a surface that reflects 90% of the light that comes in. And here along the horizon, 23.5 degrees is the sun going all around the horizon. Your south pole is straight overhead in that case. And as soon as the sun is down to 20 degrees, the energy balance becomes negative, and it starts chilling right on the surface. How fast, you say? So by sunset at the South Pole, it's already minus 80. And 3 days ago, okay, it was minus 97. You cannot melt ice from above. And the same is true for Greenland. What about Greenland? If you want to get rid of an ice sheet, you've got to spill its contents into seawater. There's no better way. Sitting in the salt water, the ice melts rapidly, icebergs calve off, they go away in a hurry. But Greenland has a mountain range all around its perimeter. It's a landlocked ice sheet. It can't spill out well. Locally it might, but as long as it's got a ring of mountain range, bathtub ring of mountain ranges around it, it's not going to go away. Whereas in Canada, it just slides off into the sea. In Europe, it goes off the Scandinavian Peninsula. It just slides off into the sea once you get into a climate that can melt it out. I ain't going to go right past that one. So what has happened to vegetation in the last, during this warming period of the last century? Well, there are trees growing above the tree line now in the White Mountains. You've seen this picture before. And that's quite exciting. You see little ones here and there. And these mature trees are all bristlecone. The problem is, all these little guys are limber pines. I can't make heads or tails out of that. It doesn't make sense. Just because they're trees rising and you get a different species, I'm going to just drop it at that point. It's very strange. How fast can trees advance upslope in timberline? Well, note this photograph. I found this postcard in the Smiley Library in Redwoods, 1885. Somebody climbed Gorgonia summit. And these little dark blips are trees. They're on the summit right here. And the next shot I took about 100 years later, and if you look very carefully back and forth, over 100 years' time, you're looking at the same trees everywhere. Nothing's changed. A guy named Bob Tosh cored a tree that's about as tall as my knee, right over here. It was 900 years old. Can you change trees very fast? Well, look at 1938, the earliest aerial photography of the region. The little black dots are trees. Here's 74, and 74 to 09. There's a little increase going on here and there, but it's really slow. Remember, all vegetation response is going to be highly lagged to the climate. That's what makes it very difficult to interpret plant cover from climate change. What about the Jesuit and Franciscan expeditions, which I've looked at really carefully? And in the Sierra San Pedro Martir in Baja California, the northernmost palm oasis described by Wenceslaus Lincoln, 1766, is exactly in the same canyon as now. And the southernmost coast live oak in this whole range of the species, which is on the west side here of the Sierra San Pedro Martir, is the same place as described by Juan Crespi. Well, you shouldn't be surprised. These trees live a couple of 100 years. So you wouldn't expect things to change very fast. There's bound to be lag effects. What about landscape changes not due to climate change? And here's one, biological invasions, which has become a huge issue here in the last 30 years. And this is California exotic annual grassland. You're looking at a European transplants here. There's nothing native about this landscape, even though you see pictures and books at the Dalton Pickwick store saying glorious California, and then they're showing you that. That's what California was like, okay? As Juan Crespi described it at Point Conception, spectacular quote, as many as the flowers we've been meeting all along the way, since San Diego, I might add, It is not as such a plenty as it is here. There's one mass blossom, great quantities of white, yellow, red, purple, blue ones, yellow violets, a great deal of larkspur, poppy, and chia. And what graced the fields most of all was the sight of all the different sorts of colors together. You couldn't have nailed it better. And flower fields like this were described all over the state by the Spaniards and later on by John Muir and other people during the Gold Rush period. And they've been replaced by these guys, especially the worst of the invaders. Red brome, ripgut brome. They're the dominant grasses in the Box Springs Mountains in our backyard. They're all over the state. And they're snuffing out our native wildflower flora. Picnic Hill, UCR. The dean lives here. As a student, we used to call it Keg Hill. Anyway, here it is in 1917, covered with coastal scrub. 1954, coastal scrub, and by 1992, the coastal sage scrub is being replaced by exotic annual grassland. Without fire, I might add, this has happened. It's competitive exclusion. This is the menace of invaders and why we shouldn't be bringing in species from other continents. Others that you may be more familiar with, right? The starling. They showed up and escaped the Bronx Zoo, and I saw them come into Long Beach as a kid in the 1950s. Yellow star thistle. The people in buildings and ground have these all over, and I don't know why they aren't digging them out here. Fennel, splitgrass in Sahara, they're really affecting the Sahara Desert. Our deserts. And to make you feel bad, threatened, pythons all over the Everglades. How'd you like to have one of those wrapped around you? White pine blister rust is invading and killing tree-lined species, pine species, throughout the western United States, especially the white-bark pine. And climate change with wildfire, this is something very close to me now. And the idea is that global warming has contributed to the recent outbreak in large fires. So, well, if that's true, it's got to be both in the United States and in Mexico. And so we will look at the San Bernardino Mountains and we'll look at the Sierra San Pedro Martir in two different management systems across the border. So yes, we've had fantastic fires over the last decade especially. And this is the great 2003 fire siege that burned 750,000 acres in Southern California in a week. The main fires, the Old Fire, Grand Prix here, the Cedar Fire here, another one here in the Ventura County. And these color perimeters that are dated here show all the areas that have burned off just since 2002. We have burned 2.5 million acres of chaparral in 9 years. At this rate of burning, our fire cycle would be 15 years. But the stuff that burned within all these perimeters was mostly over 50 years old. Something is wrong here. There are two ways of looking at it. So, well, global warming is actually making it easier to burn young stands of chaparral. The other is fire suppression management in the United States and Southern California over the last 9 years, or 100 years, has postponed burning and made these stands age and then finally break out in huge fires. And I guess another thing is, if that's true here, it should also be true in Mexico. So there you go. Big fires, border, little fires, lots of them. And they're small, even though they don't bother to put them out. There is no fire suppression down there. The reason the fires are small is because there have always been small fires that fragment the patch structure of chaparral, the fuel structures. It's a self-regulating, self-organizing system. If you have lots of fires, you preclude large ones. And the other cardinal sin of fire suppression, and by the way, here are these huge fires, 03 and 07. Nothing like that happened down here in the same weather conditions. But also, when does the burning take place? In Baja California, you can see these little smoke plumes down here. There are a couple of them. That's a typical day. You drive down there, you see 4 or 5 columns. Okay. And there they go. The smoke just goes off into the distance and doesn't bother anybody, and they're slow-burning fires. And most of it occurs in June, July, August, September. And most of the burning in Southern California and the blue bars is in the fall in Santa Ana winds. Why? You can put out all the fires you can, but you're not going to get them in the worst weather. In Baja California, the fires occur by chance, and in Southern California, we restrict them to the worst weather states and endanger society. Are we losing our forests because of global warming? So, again, the two mountain ranges. And here is the forest of these two ranges. It's the same species, same structure. Here's the San Bernardinos in 1900. Ooh. And modern picture of the San Pedro Martir in Baja California. In the San Bernardino Mountains, the forests have grown dense because there's been no burning. And I might add, Lake Arrowhead has not burned since 1879. The fire cycle is normally 50 years, and they've already gone almost 130. And in the San Pedro Martir, here's an old shot in 1903. The forest structure here about a kilometer apart, it's about the same. And the whole area is burned off. And the fires burn, kill the young trees, but leave the big ones to retain those old forest parks. But in our area, we get these catastrophic fires that, due to dense forests and the worst weather, that completely destroy whole forests. Is that due to global warming? Well, it should be happening in both countries. So here's this area since 1950 where the forests have been completely destroyed by a fire. They may have recovered some since. These areas in yellow. The forest limits are in orange. And here's the Cuyamaca State Park, San Diego County, and the Laguna Mountains here. And going across the border to here, look for the yellow. That's it. Very few places have gone through stand replacement fires. And in the San Pedro Martir, these areas. Big difference. And then finally, drought, the last one. We went through an extraordinary drought in tree die-off in 2002. It was the driest year in a long, long time. It has been attributed, and I heard this from the Forest Service 2 weeks ago, that it's all due to global warming, and they look at this widespread mortality. But you have to consider the fact that they've been suppressing fires and making forests dense for about 100 years. How do you control for that effective management? And the mortality rate's increasing. Well, of course, you're getting more and more trees sucking the ground dry with every successive year. So in Los Angeles, our very driest year was 2002, and since 1877. And the mortality, whole stand mortality, where there are no trees left inside these polygons in the San Bernardino Mountains, absolutely phenomenal. As a result of 1 year, 2 years of tree die-off, the first year from drought specifically, and the second year, a lot of insect attack. And to compare that to San Pedro Martir, it was elevated mortality, no doubt, but not the same magnitude. And at the end of all this, there's still a forest. Is it due to drought frequency? I don't think so. I'm just giving you a hypothetical profile. One thing that's characteristic about our climate, especially rainfall, is a tremendous variability in rainfall. And how often are you going to get that extreme drought, whether it's a flat climate or one of increasing temperature? The rate of extreme events is still going to be about the same. And finally, this is for the governor. Our water resource comes from mixed conifer forests in the Sierras and the West Slope. It's in red. And it looks like this, a real junky, thick forest with too many trees that have tripled and maybe quadrupled in density over the last 100 years in the absence of fire. The rainfall in San Francisco has actually kind of increased here, just like in Southern California over the last 30 years. But if you look at the runoff, there's a descending trend going on. Why? There are too many trees sucking the water out of the ground. If the Forest Service would quit putting fires out here and thin out these forests, we'd have more water yield for our aqueduct system. It's a win-win situation. Better management, more water. So I'd like to conclude real briefly here. So fossil energy technology is making humans much more powerful as a user of tools, and in combination with population growth has led to massive land clearing, destruction of wildland habitat, species extinctions, as well as biological invasions due to novel intercontinental transfer of species. All of this over the past 2 centuries. The use of fossil fuels and industrialization has increased atmospheric CO2, a process that may have contributed to modern global warming. Most predictions of future climate are made using atmospheric models, and while such models have good command of atmospheric physics, our understanding of ocean storage and transport of this new heat source is not so advanced. We need more research that links ocean-atmosphere relationships. Is there global warming? Absolutely, but it's playing out in different ways. Warming is greatest in the northern hemisphere, on the continents, in the Arctic, and least over the ocean where energy is spent into evaporation. Cooling has occurred in portions of Antarctica. If we're to have a predictor of future climate in the next 10 or 20 years, I would bet my money on ocean temperatures of the Atlantic. In biology, there's much emphasis on predictive modeling, with scenarios based on incomplete knowledge of species ecology and based on the assumption of accuracy of climate model predictions. As a scientist, this makes me uncomfortable personally when models are based on models. Error based on incomplete knowledge in a model multiplies in subsequent models. Perhaps most dangerous is the notion that present relationships between climate and the biota, for which there's an enormous body of science that has built theory to explain them, can just be dismissed because future change is inevitable. We can't toss out our baselines and empiricism out the window. I believe science needs a more retrospective emphasis on recent changes in the biota using historical data as a test for fast-forward predictions. Moreover, what have been genuine efforts to protect the biota, for example, from conservation strategies and fire suppression, have resulted in unintended consequences that are often detrimental to ecosystems and to society. Public policies in land management have recently been trumped by new agendas whereby current problems, such as catastrophic fire, are attributed to global warming. In other words, we are witnessing a political domino whereby legitimate concerns on climate have become overextended red herrings to other issues to cover the tracks of previous policy. The study of recent fire in the United States is like the fox guarding the chicken coop. The data available are records entirely within the suppression era. There is no independent evidence that separates climate effects from land management effects. Instead, we need to look at landscapes without suppression interference, such as Baja California, Mexico, northern Mexico, Canada, Alaska, or Russia. With respect to global climate change, I personally see many problems coming together, not only the potential for climate change, but also the stripping of wildlands, biological invasions, extinctions, and so on. We need new policies to tame our use of fossil carbon. We also need science that remains grounded in empiricism with respect to the effect of CO2 on global climate and its biota. Thank you. Because it's already settled land, we have no other recourse than to manually manipulate the forest. You're not going to put fire on the land there. So, but you also have a large body of people and therefore a lot of labor that could be used to change this forest. The people in Lake Arrowhead literally have to cut out 3/4 of their trees. And I don't know, maybe we need a hammer. We had a hammer during the drought. It was called a lean. When the trees died, the people in Lake Arrowhead were told, you got to get your dead trees off your property because they were worried about trees falling into other people's yards, onto power lines, onto roads, so you lose access. And so doing, the wood was cut out at a really rapid rate. But, you know, the dead trees are gone, the live trees are there, and they're still twice as dense as they should be. And it's, I just don't know what it's going to take. It's going to be, they need to be forewarned that they are going to, in 2003, I do know this, the firefighters said if that old fire started north of the lake and spread with the Santa Ana winds as a head fire into Lake Arrowhead, they would have walked away. And they would have let the whole city burn down. And that's what they're going to face if they don't do something.
Other questions?
Well, my question is that if we let all the trees burn, then wouldn't the carrying capacity of the humans decrease due to the loss of oxygen?
Okay, thanks. Probably not, because the amount of oxygen in our atmosphere is vast. So through the burning process, we take out small amounts of oxygen, and it's readily replenished by photosynthesis from plants. So in that sense, no, it wouldn't happen. Yeah.
Do you have a theory about what might have happened in the year 1977?
I think the Atlantic and the Pacific Ocean both went into different states at the same year by chance. In the case of the Pacific, we went into the warming phase of the PDO, and the Atlantic went into the positive phase of its oscillation simultaneously. And both together combined to make this. It means heat transport was getting to the higher latitudes of the northern hemisphere in both major oceans. Now think of it the other way though, is the flip side is that there's more warm water going north in one ocean, there's less going south. So the South Atlantic is not necessarily warmed up, and in fact around Antarctica it hasn't.
Yeah, it seems like this topic has become very politicized, and it seems like, just as I have a science background, graduated here at UCR, and it seems very hard to get to the bottom of like the issue as far as what we need to do as a society, whether global climate change is man-made or it's natural as we're coming out of ice age or whatever. But it just seems like because there's so many political charges with each side of the argument, it's hard to like kind of wade through all the baloney and get to the like real truth and like what do we really need to be doing as a society as far as to what's the best way to handle the situation, I guess, and kind of set aside our political agendas. So I just wanted to see if you could maybe comment on that political aspect of this whole discussion.
I have two answers right off the bat. One is that it is important that we are discussing all these issues. Can't hurt. Hopefully, eventually, rational people will come with the rational answers. The other thing, and it's really, my daughter's going this way, is that we need a new kind of media called scientific media, where we get people who know science and also want to get into the media side to document these things far better than what we normally get in the media. And the newspapers in particular, you have journalists that do what they do, they're supposed to do, but they're not necessarily trained in science, and I think there's a lot of knowledge that's lost in the process. No comment.
Yeah, I'd like to go back to the local issue in Lake Arrowhead. During the old fire, we lost, so many trees in the bark beetle infestation. I guess my comment then would be, wouldn't that increase the amount of infiltration as far as tree rain and overall precipitation into the ground, adding to the aquifer?
There's some ironic benefits of this drought. First of all, the mortality was fundamentally a drought-produced thing. The insects have always been there. They never invaded the place. They just take advantage of a condition where the trees are highly stressed. And ironically, the forest densities have decreased enormously as a result of that drought. Unfortunately, the dead fuel buildup in the litter is still all there, so you still have a flammable situation. However, because there's less living, there's actually more water yield that's going to take place as a result of that.
A follow-up would be, where's all the water?
The water is, it goes down the creeks and down into the watershed. That's the old saw. You have a fire and suddenly this creek shows up in a watershed. It happens all the time. This transpiration is the last part of the hydrologic cycle that was understood really well by science. Yeah. It's too bad that water is invisible, or else we would have discovered it a lot earlier.
And lastly, that's true, very much true. The policies that we have up in the San Bernardino Mountains, as far as your CCRs and your, for example, the Arrowhead Woods Association, prohibit anyone from cutting trees larger than 6 inches in diameter. And they have complete control over the tree issue up there. And so it's prohibitive for people to thin their property. And I'm only talking about in the incorporated areas. Is there a change, or is there any data that could be supplied to Forest Service personnel in which we can start thinning that stuff out?
I'm glad you asked that. We have a very good database from the San Pedro Martir of what a forest should look like, a proper forest. And what you should be thinking about is 40 trees per acre, plus or minus 20, and the density is, and the tree stems are mostly 2 feet and more in diameter. That's your goal. If you've got a half-acre property, you shouldn't have more than 20 trees and almost nothing small. You've got to have a baseline as a goal, and so your question was perfect because I was waiting for that, or else I would have brought it up. People don't know where to set up law and how to tell people how to deal with their forests unless you have a baseline. So right now, Arrowhead, their places in Arrowhead are running 50 to 1,000 trees per acre, and I'm not even counting the little guys. And it should be 100 per acre, much less. And more in the, and that's, in the San Pedro Martir, that's generally what it's running. 100 per hectare, 40 per acre, the numbers it should be. Any ranges in the San Pedro Martir, in white fir forest will be up to 100 per, almost 200 per hectare, or 80 per acre, but more like typically 30 to 50. Big trees, umbrellas, and more importantly, this is another thing, you need to trim and limb them up as high as you can, 5 to 10 meters. Our mature forests down there on the Mexican side have all been limbed up, and pine trees don't bud out again after the fire. So once they've been limbed up by a fire, they stay limbed up. And so it's not just density, you've got to get the canopy well off the ground, and nothing in between. You don't want that fuel ladder. How does it? Well, that's fine if you don't have a land use issue. And a lot of the San Diego Mountains are empty, and I think we have opportunities whereby we should be running fires through it. San Gregonia Wilderness, why not? It's a wilderness area, for goodness sake.
Other questions? If not, let's thank Rich for a very interesting talk.
Thank you.